All right, good afternoon, everyone. Welcome to Elasticon, and today we're going to talk about scaling network insights with OpenNMS and Elasticsearch. So we're going to talk a bit about our journey, of course, using OpenNMS and Elastic to manage flows. So a bit about me. I'm Jesse White, the CTO of the OpenNMS Group. I'm founder of the OpenNMS Group Canada, where I'm located here currently in Ottawa. And I actually started as a user and community member of the project. And I was the lead architect and developer on the flow integration that we're going to talk about here today. Okay. So in case you haven't heard about OpenNMS before, OpenNMS is a scalable network monitoring platform used by large enterprises to monitor their networks, typically used in large enterprises, of course, talking about hundreds or thousands of devices, right? It's an extensible platform, has lots of hooks and integrations to talk to other tools in the ecosystem, including Elastic, of course. It is open source and published under the AGPL v3 license and is supported by the company and group here at the OpenNMS Group. So like I said, today we're going to talk about network flows. So before we go that, about the solution, let's understand a bit what flows are, right? So flows are typically generated by NetFlow enabled devices. So what they do is they take in network traffic, right? And as traffic goes through the devices, we're talking switches, routers, they'll inspect the packets, look at the header information, and then create a cache from that and summarize some of the key statistics around the packets. It doesn't actually look at the data or the body of the packets themselves, just looks at the kind of attributes and header information, and then generates what we call these flow packets. They're from those and send them to flow collectors, right? So that when we're talking about network flows, we're talking about these flow packets generated by these NetFlow enabled devices. So why do users even care about flows? Well, as we know, networks are complicated. There comes to be a lot of problems with networks, and then flows help us give additional visibility, observability of our networks, and help us give up more information around what's going on, right? So help us give some additional insights, what's happening, and give network engineers additional tools to figure out what the problem or source of the bottlenecks are. So how does the solution actually work, and what did we build? So this will be looking at the first generation of the solution. So we do on the left-hand side, we do have those flow exporters, again, the NetFlow enabled devices. So they end up sending the raw flows to a component that we call Minion. So that's basically our agent or collector. It ends up receiving those flows and then does some level of DNS enrichment there as well. So it'll do reverse lookups on the IP addresses to figure out the appropriate host names. These agents are typically deployed at remote sites or particular locations. So the DNS records there may be specific to that site, right? So once it retrieves the flows and does the enrichment, it'll forward them onto Kafka and then normalize the flow format. So flows come in different flavors, different protocols, NetFlow 5, 9, IPFix, SSFlow, et cetera. So we're able to canonicalize those, have a standard format, put them on Kafka. We then have a process that we call the Sentinel that enriches those flow records and is able to process them and do things like inventory mapping. So determine what device in the inventory it's associated to. Does things like application classification. So what is the flow about? Is it HTTP traffic, a backup job, et cetera? And we're also able to perform thresholding on it. So looking at things like, if total flow if backup traffic exceeds a certain percentage of the link, then generate an alert, right? So those are some functions there done by Sentinel. And then finally, the flow records get indexed into Elasticsearch. Right, so that's the full write path and the journey they go on. So again, the minions are typically deployed at remote sites, locations, or within data centers, and then the sentinels are used to process those and then index them into Elastic. So that was the write path. Now, if we look at the read path, the way users typically look at it, they'll interface with either Kibana or Grafana. Grafana, we do have a custom plugin or application that can use to query OpenNMS core, which then ends up doing read queries to both PostgreSQL and Elastic. And you do see noted on Elasticsearch, we do have a plugin indicated there as well. So we'll cover that in a couple slides later, this drift plugin. So those queries to Elastic are pretty heavy on aggregations and end up doing some top case statistics over top of all the flows with the intent of generating kind of these network graphs, right? And then similarly, you can use Kibana, looking at the indices directly, and use all the powers and visualization tools that we have there. So that said, here's what it kind of looks like whenever users interface with it. So this is a Grafana, little animation of a Grafana panel. We have a user kind of zooming into the data. As you see, there's a lot of the kind of rich detail that's shown here. So this is total bytes in, and we're able to map the different applications, who the top, what the top applications that actually using the bandwidth on that link. Now, what's interesting is the actual resolution of this. You see, we have a fair amount of detail, and then right now we're looking at seconds, and then we're able to zoom into those to get kind of millisecond level details, again extracted from the flows, and that's achievable in part by the degree of precision that we have there through the instrumentation, and also that plugin that we did implement there with Elasticsearch to be able to kind of again keep the details of the flows that we have. Again, we're able to get rich detailed information, down a millisecond level just there from the flows. So without flows, if you're to just use other tools like look at interface counters and the like, you're limited by the scrape interval that you have configured there, right? So in this case, we got data showing up every 5 minutes. You could see that things are using the link, of course, but you'll have a bit more difficult determining what's actually out there, right? So flows can tell you what, and again give you that high degree of precision around what's actually utilizing the link. Advantages over SNMP data. So did mention that custom plugin, right? So why did we implement that? Why do we need that? So what we found is that flows are actually ranges. So what a flow will tell you is that this many bytes were transferred from this time between these two times. So fields typically called first switched, last switched, so that the first time a packet was observed, it's associated with the flow, and the last time a packet was observed, associated with the flow. So it ends up being a time range, right? And then what we found by default is that documents are, treated as a single point, right? They only have one timestamp that can use for, bucketing in the aggregation. So what we did was we wanted the buckets to take into account the proportional sum or the proportional range that the flow intersected with the bucket, right? So if, for example, we said the flow had 100 bytes and that whole flow time ranges were in the bucket, then we wanted to consider it all. If it was only intersected half with the bucket, then we wanted to take 50% of it, and so on. So what we ended up doing was creating a custom plugin that allowed us to achieve that behavior. And that helped us get that extra resolution there that we saw in the graph with the flows, truly being able to treat them as ranges rather than single points in time. A couple links at the bottom there, the actual implementation of the plugin and some of the discussions that were done around it there in case you're interested. So here's some idea of what the scale that enterprises need and some statistics from some of our clients. Right, so we do have some enterprise customers that have hundreds of routers generating these flows, with 1 or 2 interfaces on these routers being configured to generate those flows. So those typically the links that connect out to the ISP or WAN circuits, and then some of these generate roughly, let's say, 6 million flows per interface an hour. So as you can get an idea of the scale here, these are hourly indices in Elastic. We're seeing over 100 million documents there per hour and roughly 80 gigabytes or so. So that was in some, kind of early statistic snapshots. The solution has actually been deployed many more, places there since. We're now seeing deployments with hundreds of thousands of flows per second and doing billions of documents per day. I think roughly 8 billion or so in some cases, and then generating again like terabytes of data per day in these indices. So the volume of flows can get quite large in these bigger enterprises that want visibility on all their network traffic. So that's fine and well. Like mentioned, that was Gen 1 of the solution, right? So when we got to actually deploy this in production, we did run into a few problems, right? First, we found that we couldn't respond to many of the queries fast enough, right? So if you were trying to generate, let's say, reports around trends, looking for days or weeks, some of those queries actually took like 30 plus minutes to render. We ended up tweaking, timeouts on all the different services, et cetera, but still couldn't cut it. And then the customer requirements, we want to be able to render dashboards, looking at recent data. So let's say 4 hours and 10 seconds or less, very reasonable. And reports that were, 30 days, for example, in 10 minutes or less. So those typically queried by batch jobs. So, responsiveness didn't matter too much, but you still wouldn't want to wait hours there for those to be generated. So those kind of requirements, what they translated using the scale and volume that we just talked about, trying to use Elasticsearch to do top N over billions of documents, right? In the fields that we're, aggregating on, we're talking about, hundreds of thousands of unique hosts and applications. As we know, IP addresses, ports, a lot of uniqueness there. So, quite a complicated problem to solve. So there's a link there at the bottom to give you some idea of what the queries look like there as part of our solution. So we set off to find a way to kind of solve these and meet the requirements. So this is how we adapted. So you see a new component there introduced at the bottom. Feeding off of those flows in Kafka, in addition to sending them to Elasticsearch, we would also send them back to Kafka, fully enriched, and then use an Apache Beam application on top of Flink to perform the aggregation, right? So this would pre-compute some of the statistics around the flows and top K, et cetera, such that it would make it, easier to query, right? So we'd store these aggregated flows in an alternate set of indices there in Elasticsearch that would have, some of the same characteristics as the raw ones, but allow us to generate those reports much quicker, right? So that, of course, added an additional component, another cluster to the stack. As you can see, there's lots of JVMs here in this diagram. You can imagine what this looks like. So it did, add a bit of complexity there to the solution. One thing that was pointed out as well is that, it may be possible to actually do that with ingest pipelines into in Elasticsearch instead, something to consider in a future iteration. But the way it was implemented here, using an Apache Beam pipeline, again, calculating those statistics, putting them in Elasticsearch as a set of alternate indices. Now, on the read path, very similar diagram before, no new components there, but some intelligence added query time that would be able to determine whether or not to use the aggregated indices. So if the time range, for example, is greater than a day with some configurable threshold, then you'd fall back to using the aggregated indices. You'd lose a bit of that granularity, but then your queries would come back faster. Right? So with all that, we were able to finally achieve scalable ingestion into Elastic. We're able to see hundreds of thousands of flows per second using completely open source components, from ingest all the way to indexing and visualization. We're able to achieve, very high precision, by, again, keeping the flows and timings, and then, treating them truly as ranges, even when doing the aggregation, and bring that information back to the user. And we're able to achieve speedy reporting. So our network operators would be able to get, quick overviews of seasonal trends and insights, even over large ranges of time, without, having their queries time out on them. As part of this process, here's kind of some things that we learned. We learned that Elastic is truly scalable, right? So we're able to ingest again hundreds of thousands of documents per second, provided there was fast enough disks and enough nodes. Anything we threw at it, it was able to handle. It truly was extensible and that we hit a case where we needed different behavior, right? And we wanted more precision, so we ended up writing a plugin and extending the platform, right, to achieve what we needed. We did find through performance tuning of our application that batch inserts and asynchronous APIs were the way to go. So we had a lot less waiting, less round trips there. We're able to get the throughput that we needed. Did find that query optimization has its limits. So again, there, no matter how much we tried to optimize those queries that were 30 minutes or more, we just weren't able to get them there fast enough. So what we ended up having to do was pre-compute some of the data, pre-aggregate it, and do that as part of the ingest path to be able to get the read performance that we're looking for. And finally, note on flows. Even though there are standards, they do differ, greatly by vendor, with slight implementation details, missing values, missing timestamps, you name it, we've seen it. In some cases, we even found, bugs in, large network vendors' equipment. So, for example, there was a case, I think, where the VLAN header was not being taken account in the offset properly. So when it was looking at the IPv4 header or IP header, it was confusing some of the values, and the details we're getting back were corrupt. So through this, we're actually able to improve some of the networking equipment out there, and then have a solution that's truly able to ingest it all. So that said, that's all part of the OpenNMS Horizon platform. Again, if you're interested in flows or getting additional visibility on your network, feel free to try it out. It is free, open source, and you can give it a spin on your network. So that's it for me today. Speed run through our flows. Hopefully you learned something new here, and a bit of what we do here at OpenNMS with network visibility. So thank you for your time, and happy to take questions with the time that remains. A minute, see if anything comes in. So thanks for the kind words, everyone. Thanks again. It was fun.